here's the norm helping us out one more time. It's like Cheers. Norm walks into the room and everybody is happy. So norms are incredibly useful, and 135 is a perfect example of that. So group that did 135, what did your logic look like?
We started with let z of square root of d be a quadratic extension ring in an element.
Okay.
And we assumed that the norm of z was equal to plus or minus 1, and then we proved that z was an element of the ring, and that it was a unit. So we just took the definition of the norm, and that it was z times the conjugate.
Ah, okay, great. So if z belongs to this ring and its norm is equal to plus or minus 1, then you're saying by definition of what the norm is. Yeah. So this is where we benefit from specifically being within the quadratic extension ring z adjoin d, because in that ring, the norm is defined exactly to be the product of z with its conjugate, where we know what the conjugate is. We just take the square root of d and we flip the sign on it. And it's because the norm is defined in that way, you're saying that this gives us an equation, z times z bar is equal to 1. But then what does that imply?
Then we multiplied both sides on the right side by the inverse of the conjugate.
By the inverse of the conjugate.
Proof that the conjugate is the inverse.
Okay, I like the idea. Because where you're going with this is you're trying to show that, at the end of the day here, that z bar is equal to z inverse, right? So I don't take issue with your conclusion whatsoever. What I am interested in hearing from all of you is, why am I going to say that it's not kosher for us to just multiply by z bar inverse on both sides of this equation in order to get from there to there?
Do we not know if there is a z bar there?
Yeah, that's my point, is that we don't know that z bar is a unit. We don't even know that z is a unit. After all, that's what we're trying to prove. We're trying to prove that z is a unit, and you're doing so, wisely, by trying to demonstrate to us not only that it has an inverse, but demonstrate to us what that inverse is, which is a great idea. It's what we call a constructive proof. It not only shows the existence, it demonstrates the existence of something, in this case, that inverse. And so I think that you can fix your proof not with a pen, but with an eraser, which is always a good idea, if you're using erasable pen, I suppose. And my point is that we can go directly from the line on the left to the line on the right, up there. Directly from the knowledge that z times z bar is equal to 1, to the conclusion that z bar must be the inverse of z. What is it that allows us to go straight from there to there? Yeah, it's the definition. And it's the definition of an inverse. Right? If there is an element, z inverse, then that element is exactly the element that we see here. The element which satisfies, when I multiply it by z, the result is equal to my additive identity 1. So, whatever that step of logic that you added in to go from the equation on the left to the one on the right is, yes, a hasty assumption because we were assuming z bar was invertible. But not only that, it was unnecessary. So get rid of it, and the rest of your proof, awesome. It looks great. So the norm is great because it completely characterizes for us those elements that are invertible inside of a quadratic extension. So what you've proven here is just having a norm of plus or minus 1 automatically guarantees that an element is invertible, that it's a unit. There was also a backwards implication. Can you walk us through how the reverse direction goes?
So we started with the same thing, we started with let z times z inverse equal 1.
Okay, so you're saying let's suppose that z is a unit.
Okay.
Got it. So now we're going the other direction, and we have to prove that
The norm is equal to plus or minus 1.
there we go. We need to prove that the norm is equal to plus or minus 1.
We started by taking the norm of z times z inverse.
Okay.
And then you can make that into the norm of z times the norm of z inverse.
This is why norms are so useful, is because of that property. Okay.
Makes them into an integer, and since them times each other equal 1, they both have to equal 1.
Okay. I don't think I left enough space here. Let me make a little more room. So why is it that this must equal 1? You started with z times z inverse. But what is z times z inverse? It's 1. So this we know because we assumed that z was a unit, and therefore this z inverse element exists. And then when you took the norm of z times z inverse, that's the left-hand side of this equation. But because it was an equation before you took that norm, the norm of the left-hand side has to equal the norm of the right-hand side. And then your logic is that, well, now we can split these norms into two pieces. Oops. The norm on the left-hand side, the norm of a product, is the product of the norms. So n of z times n of z inverse. Equals the norm of 1. But what is the norm of 1? It's just equal to 1. Again, multiply 1 by its conjugate, but 1 happens to be its own conjugate. And so we get a 1 on that side of the equation. So now we're back to where you were a moment ago. Now we know that n of z times n of z inverse has to equal 1. And from that you conclude what? Z inverse was the conjugate of z. Oh, so were you using that to change this second part of the equation? Let me take just a quick step back to make an observation that you made a moment ago, and I want to amplify because it was an important observation. When we started with the equation z inverse is equal to 1, that was an equation that related together elements of our quadratic extension, z adjoin radical d. And that's, not an obvious friendly set. It's not one that we work with all the time. But after we take the norm of both sides, what kind of elements are we working with? Integers, exactly. And we happen to know, usually from a very early age, quite a lot of facts about the integers. So anytime we can turn a question about a difficult set into a question about a set that we understand a lot more about, it's a good idea. And this is really one of the reasons why the norm is so useful, is that it allows us to do this kind of thing. So now the equation that we have on the bottom is an equation that has only integers in it, and no longer any more elements of z. So the norm of z is an integer, and the norm of z inverse is an integer. And when I multiply those two integers together, I get 1. So what does that tell us about those integers? Yeah. Yes. Well, let's see. Yes. Yes, you're right. In particular, it tells us that the norm of z has to be invertible as an integer, right? Norm of z is an invertible integer because there's something that it can multiply by to become The integer is multiplicative identity element 1. But we know that the only invertible integers are plus minus 1. Completing the proof. Awesome. So this is a strong theorem and a strong proof. It shows that all we have to know about a quadratic integer is that its norm is plus or minus 1. If we know that fact, then we can guarantee that it is a unit, and vice versa, that there are no other units out there in the universe in z joined square to d, other than the elements that have norm plus or minus 1.